Yeah, so it's wonderful to be here. I'm really excited to spend part of my sabbatical here and learn more about what you guys do. So today I'm going to talk about this recent work we've been doing in my lab on large-scale topic models and efficient inference for those. But I'm going to start by talking about AI a little bit. So you imagine an AI system, right? One of the things we'd like an AI system to be able to do is answer questions like this that require some amount of world knowledge, right? So we'd like a user to be able to come and say, tell me some things that a person can throw, and the system should just be able to name some things, right, that a person can throw. So this is one of the things, right, that we'd like an AI system to be able to do. So we could, one way we could imagine encoding this task, formalizing it, right, is that we have a relation throw, and we want to know, what are some things that a person, what are some things X that a person can throw? And, right, this is, the classic AI approach to solving this problem is we might write down, some horn clauses that say, well, if a person's going to throw something, it can't be that heavy, and it can't be like, 30 pounds of atmosphere. It has to be like a relatively localized thing. And, right, if all these conditions are met on a thing X, then we say a person can throw it. And if we have a knowledge base with enough knowledge about objects, right, then we could conclude, a baseball can be thrown. So, right, what's hard about this is it's really hard to encode all the knowledge. You might be able to do it for throwable objects, but then can you do it for insects and films and blah, blah, blah. So any question that might come up, it's hard to encode enough knowledge that would actually accurately answer all these questions. Okay, so the approach that motivates most of the work that I do is encapsulated in the following other technique. Right? So we could also have a system that instead goes to the web and queries for this phrase, throwable objects such as. And sort of amazingly, and what I love about this is like, why would anybody ever need to use this phrase, right? But sure enough, it is used hundreds or thousands of times. And each time it occurs, right, we get examples of things that can be thrown. So this approach, right, can immediately allow us to arrive at hundreds of throwable objects, and a bunch of systems were built to exploit this this intuition that there are certain phrases that are where the semantics is actually very easy to interpret, and if we use something like the web, right, we can actually get great power out of this. So it's easy to immediately arrive at hundreds of things that can be thrown, right, without really doing a lot of reasoning. Okay, but hundreds of things that can be thrown is actually a vanishingly small fraction of all things that can be thrown, right? So in truth, there are millions of throwable objects. And this approach, while it's surprising that it yields hundreds of throwable things, it certainly doesn't yield all of them. So a lot of the work that we're doing in my lab focuses on trying to push this strategy further by getting better estimates of what X's are likely to occur in phrases like throwable objects such as X, were the web to increase, say, 100-fold in size. So this is what's known as the statistical language modeling task, right? We're trying to assign probabilities to sequences of words. And what we'd like is, a distribution over all possible X's, millions and millions of possible X's that could occur there, even if we've never seen a particular X in that context, right, in an actual body of text, even as large as the web. The way we can do that, right, we're building probabilistic models. We want to build models that can pick up on clues that sort of look a little bit like world knowledge, but they're really just about regularities and sequences of text. So if we see I picked up the X a lot, all else being equal, that makes throwable objects such as X more likely to occur, right? And this is something that we can learn just by iterating over bodies of text. This approach just uses text, right? So we're not committing to any kind of logical encoding of knowledge. So there's no knowledge representation scheme that I'm committing to in this approach, although there are assumptions that we're going to commit to in terms of the models that we build. And I'll get to that in a second. But one of the advantages of this approach is that you don't have to commit to a knowledge representation scheme. And, of course, any running text is training data for these models, right? So if you can just get running text, and there's a lot of that already, and more of it being created every day, you can create new training examples for this approach. Okay. So a little bit about my lab at Northwestern. We call ourselves the Web Scale Artificial Intelligence Lab. I'm fortunate to work with a set of really good PhD students. We have a couple of alumni. This Brent Hecht was not advised by me, but I'm going to talk about, we worked closely together while he was at Northwestern. I'm going to talk about a project we did that we're still working on, actually, later in the talk. We focus on a handful of things. So we're trying to build better models of text. So that's a lot of what I'll talk about today. We're also interested in applications of those approaches, and I'll show you one of those called Atlasify later today. So I should also mention there's a distinct application that I won't talk about that Chandrasekhar Bhagavatula, who was just here, right, worked on, right? And so Chandra's last day was was last Friday, and he's not here today, which is fortunate for him. He missed his advisor being in town, but he worked on a technique for mapping strings in tables to their referent Wikipedia page, and that's what he's presenting at the Semantic Web Conference. And that's a technique that works really well. So this work of his that you guys may not have heard of, although I know he really enjoyed his time here. Lastly, I'm really interested in human guidance. So one of the things we work on in our lab, most people train language models just by taking what comes in a large body of text, right? But I think we might be able to do a lot better if we ask people specific questions about what text is more likely to occur. And we've done some work in that direction as well. And that'll appear at EMNLP, which happens in about a week, actually. All right. So now, I'm going to give you guys a little bit of background. But before I do this, let me do like a show of hands question. So, and Chandra warned me that this material would be very familiar to you guys. How many of you guys would say you're familiar with the notion of word embeddings? Okay, so almost everyone. And how many of you would say you're familiar with latent Dirichlet allocation? All right, so almost all of you. Okay, we'll go through this quickly. I want you to, so there are some things that I'll tell you about sort of my take on both of these things. And I'll make sure we're all on the same page about that. But I won't belabor it. All right. So, word embeddings. The best language models, so the best models for assigning probabilities to sequences of text do two things. They learn n-dimensional numeric vectors that represent words, right? So we're going to, and think of n as being like 1,000. So we learned 1,000 dimensions for each word. So, man has a vector and woman has a vector. And then we learn a generative probabilistic model that uses those embeddings to predict probabilities of sequences of words. And now here's something that, right, even though you've heard of word embeddings, you may not know. This idea, right, is actually as old as the hills. So in particular, hidden Markov models, right? The Baum-Welch unsupervised algorithm for learning hidden Markov models does exactly this. And, it was invented in, about 1970. Although it doesn't come up a lot in this sort of discussion of word embeddings, which I think is a little bit unfortunate. But it really is, as far as I know, the first sort of sequential model of learning a probabilistic model of text that uses, right, these projections to n-dimensional space. And, right, one of the nice things about these models is that the word embeddings themselves carry some information. So words that are similar, right, tend to be in similar points in this high-dimensional space. And that's because words that appear in similar contexts tend to be in the same place in high-dimensional space, and meaning is related to context, right, via the distributional hypothesis. Recently, right, the fact that the word embeddings seem to reflect analogical information was, discovered and this was very provocative, that, analogies between word embeddings. Here we're visualizing these word embeddings in the two-dimensional space of this slide, right? And it seems like there are regularities between the vectors that reflect an analogical information. So man is to woman as king is to queen. And this kind of, right, is not as true, maybe, as this graph makes it look. And there are caveats to this. Like in particular, if you follow this vector from man to woman and this vector from in the same direction as man to king from woman, you're actually just as likely, in my experience, you're just as likely to land not at queen, but instead one of these original 3 words that you started from. That's something that's actually, right, it's mentioned in the papers, but not a lot of people realize that. So there's, this graph is a little bit of an idealization, but nonetheless, this is sort of much more true than you would expect. It's sort of much more true than I would have expected, I guess, before Mikolov introduced that insight. Okay, so here's what I'm going to talk about today. So this is our work, is improving on what I'll call flat word embeddings. So with very few exceptions, the embeddings that people project words into are flat in the sense that the dimensions are exchangeable. So if I took dimension I and dimension j and renamed j to be I and I to be j, I could get exactly the same model without having to touch any of the other embeddings. So that's what I mean by exchangeable in this sense. This seems like a mistake, here's why. So I'm going to ascribe some meaning to the particular dimensions of these vectors, which is a little bit of a fiction, but allow me some poetic license. This phenomena that I'm describing is going to be bona fide, even though ascribing particular semantic meaning to a given dimension of the vectors is a little bit unsafe. But let's just say that there's a dimension that represents, here's a player that plays for the Cleveland Cavaliers, and there's another dimension that represents whether somebody plays for the Chicago Bulls. And we have 2 players that we're thinking about the vectors of, right? Pau Gasol and LeBron James. So they're both active for this NBA topic, right? Because they both play for NBA teams, but then they're active for different particular NBA teams. So these vectors could capture the meaning of these 2 individuals, Pau Gasol and LeBron James. Pau plays for the Bulls, right, and LeBron plays for the Cavs. But the problem with this representation, right, is that anybody who plays for the Cavs is also going to be active for this NBA dimension, and the model doesn't reflect that, right? So there's actually, these are separate independent dimensions that have to be learned separately, and the regularity that anybody who plays for the NBA, any one of these NBA teams is going to be active for this NBA topic is not reflected in the model. All right, so this is the incremental step that we're taking in terms of the formalization of the learned embeddings. We're going to learn hierarchical ones instead. So instead of thinking of a large set of exchangeable dimensions, we're instead going to think of all of these dimensions as being part of a large hierarchy, and I'll show you exactly how that works in a second. But the basic intuition is that Pau Gasol is going to map to the Bulls topic or Bulls dimension, and that's going to be a sub-concept of NBA, which is a sub-concept of sports and so on. So there are 2 reasons why you want to do this. One is that this is actually how word meaning tends to work, right, in the real world. So words actually do have these sort of subsumption properties to them. This also improves model accuracy. So one way to think about this is when we have enough information, so for somebody like LeBron James, who's very famous, we can actually model him at a very high level of granularity. Someone like Pau Gasol, who is a little bit less famous, maybe we actually don't have enough data, right? So, ZIF distributions of text being such as they are, there are a lot of terms, even in a huge corpus, that don't occur very often. Maybe we can't necessarily conclude that Pau Gasol is an NBA player, or sorry, that he's a Bulls player, but we might be able to model him appropriately at just sort of slightly less precision as being an NBA player. Okay, so that's the idea, and then so we can use these hierarchies to model things precisely when data is plentiful, and then back off to more coarse-grained models when data is more sparse. All right, so here's the setting that I'm going to talk about today is in the case where the embeddings are large and sparse. So a lot of the dimensions are 0, and the number of dimensions is large, and we're going to get up to like 1 million dimensions. The canonical example of this is when you're doing latent Dirichlet allocation with Gibbs sampling. So the 2-minute version of latent Dirichlet allocation, it's a generative model of documents. We assume documents are mixtures of topics. Topics are multinomial distributions over words, right? So each one of these topics, this is a genetics topic, this is a computers topic. They have certain distributions over words. Each document is a mixture of topics, right? The way we generate a document is by picking a topic for a given token. And we pick that from this multinomial that describes the document over topics. And then once we've picked our topic for a given word, we then pick the word from that topic's multinomial, right? We do this, n times for a document that contains n words, and we end up with a document. Right now, we're ignoring word order, right? So we're just treating the document as a bag of words. And that's what we'll do for the rest of this talk, but actually the models I'm describing can be applied to word order, and that's, I'll mention something about that at the end of the talk. So of course, when we're doing latent Dirichlet allocation, right, all we get is the raw text, and it's our goal to infer what are these multinomial distributions over words, what are the distributions over topics for the document, and then which topics correspond to which tokens. And we can give these things Greek names, although we don't really have to worry about that right now. Just remember that the setting, the variable z is going to refer to the particular topic settings of each token in a document. This is the Gibbs sampling approach for learning these distributions that I want you to have fresh in your mind. So we start by initializing all these topic variables randomly, right? We set each of these zi's for each token I to some random topic from our set of topics. And then we do these sampling passes over the corpus. So for each one of these tokens, we refresh our estimate of what zi is based on every other setting zi in the corpus. Right? How do we do that? Well, we multiply two factors. Okay. So, and this is the key multiplication that is often slow, that we will talk about how to make fast. And this is the thing that the sort of technical meat of the talk is operating on this multiplication. So it's worth making sure this is fresh in everybody's mind. So the idea is when we're trying to compute this new topic distribution, we take into account two factors. One is whatever the document tells us about which topics are more likely, and the other is whatever the word tells us about which topics are most likely. And that information about which one is most likely just comes in terms of the proportions of the current state of the sampler. So across all these z's that we've assigned, we count up how many times does this document use a particular topic z? How many times does this word use a particular topic z? And the probability that we select that z is proportional to those counts, right? Smoothed by these Dirichlet hyperparameters alpha and beta, right? Because we don't want zeros, so we use these alpha and beta hyperparameters. And the larger they are, right, the more uniform the distributions that we're drawing from. Okay, so everybody's up to speed on LDA with Gibbs sampling? Okay. Oh, and right, and so LDA, right, is, it works. You can learn fairly good topics. Over, right, in a totally unsupervised fashion over text. Okay. So now let's talk about hierarchies. So this is now our new work. So there's a funny thing about how people use topic models in practice, right? Even if you'll see a lot of people work with data sets the size of Wikipedia, but they'll still actually use relatively small sets of topics, like 200 or 300, which seems to not reflect the actual reality of the corpus, right? Wikipedia has 4 million pages, and you could think of even each one of those pages as being essentially a topic. So it seems like data set the size of Wikipedia, you'd want to use hundreds of thousands or millions of topics, not a few hundred. So why do people use small topic sets? Well, there are two challenges, right? One is that we run into computational complexity. And in recent years, a lot of work has been done to attempt to extend topic models like LDA to large sets of topics. So sparse LDA and alias LDA are two relatively recent techniques that allow you to learn LDA models over huge sets of topics, but there's another problem, right? Even if you can scale computational complexity-wise, you run into this data sparsity problem, right? So if you have 1 million exchangeable independent topics and you're trying to estimate, for a word that occurs a few hundred times, whether it falls into one of those particular topics, that's actually incredibly hard. So your data is very, very sparse for rare words, short documents, rarely expressed topics. And so LDA tends to become less accurate. Even if you can scale computationally to large sets of topics, it becomes less accurate because of data sparsity. So where our work falls is in trying to use hierarchical organizations of topics to overcome the data sparsity issue, of which there are several sort of existing variants, but these ones don't scale to large sets of topics. So as the number of topics gets large, these existing hierarchical topic models, which have been proposed recently, tend to slow down too much to be applied to large-scale corpora. So our work, right, falls into this area where we can use a large number of topics, like are actually expressed in large corpora, and we can overcome data sparsity by using hierarchies. All right, and the idea behind this is actually very simple. And so I can really describe everything about the idea in 5 minutes or so. So that's what I'll do. So LDA gets its name from this thing, right, the Dirichlet prior that it uses. We're going to use a different prior. So we're going to swap out the Dirichlet for this thing I'll call a Sparse Backoff Tree. And for the purpose of the next 5 minutes, think of a prior as transforming a discrete set of counts into a probability distribution. So here's the Dirichlet. Here's what it does, right? And let's just think about the probability over a random variable given a set of counts that we've observed. And this is just one of those terms, what does the word tell us about the document? What does the word tell us about the topic? What does the document tell us about the topic? This is just one of those. So think about this as the document distribution. And in this document, the current state of the sampler tells us we have 1 occurrence of topic 1, 2 occurrences of topic 4, 1 occurrence of topic 5, and 1 occurrence of topic 12. So what the Dirichlet does is turns these counts into a probability distribution. It does that by adding this hyperparameter alpha to each one of those counts, turning those into pseudo counts, and then the probability distribution is proportional to those pseudo counts. We just add them up and renormalize, right? So this is how we get a distribution out of a set of counts in the Dirichlet prior. All right. Right, and where does this 1.2 come from? Well, the 1 is the count, and the 0.2 is the alpha, and right, that gives us a distribution. So the upshot of this is that the larger the NZ is, so the larger the count that we've observed, that we have in the current state of the sampler, the more likely something is to be sampled. And we know if we use a Dirichlet prior over a relatively small set of topics, we can end up with a nice topic distribution for a document, right, by incrementally or by iteratively applying this sampler. All right, so here then is our proposed alternative, which we call sparse Backoff trees. So sparse Backoff trees begin with a tree structure. So assume this tree structure is given to us in advance. We've said, there are 12 topics as before, but we're assuming that the first 3 topics are related to each other in a particular way, and the first 6 topics are more related to each other. So topics that are closest to the first 6 topics rather are more related to each other than they are to the second 6 topics. So think of topics at particular points in the tree as being more related to their neighbors than to topics at a longer distance. And again, we're assuming this tree is given to us in advance. We just write this down in the same way that with Latent Dirichlet Allocation, we pick a number of topics like 500. So we assume there's some tree structure, and we're going to try to fit the actual meaning of these topics into a tree structure of a particular type. So, by the way, this is actually a pretty big assumption that we're assuming we know this tree structure. Although if you use a large enough number of topics, you're actually not committing to too much when you write down a particular tree structure, but this is an assumption that we'd like to weaken in future work. This does help us to scale. So for right now, let's assume we're given this tree structure. And then we have a different set of hyperparameters. So we have these deltas at each interior node. This replaces the alpha in the Dirichlet prior. So how does delta work? Well, here's what it does. So each one of these interior nodes subtracts a value delta from its non-zero descendants. So this 0.36 is going to be subtracted from each one of these non-zero counts. And then whatever this interior node subtracts from its non-zero descendants, it then applies uniformly, right, to all of its descendants. So it takes from the halves and gives back to everyone. That's what these interior nodes do. And then the result of this is actually that nodes with non-zero neighbors tend to get higher probability than nodes with lots of zero neighbors. And here's an example. So this 0.46, where does this come from? Well, it's 1 minus, so each one of these interior nodes is going to take away from this one. But then each one of these interior nodes is going to give back a smaller amount. So this 0.1 divided by 3 comes from this node that took away, 0.3 divided by 3 comes from this node that took away 0.3 and then divided that equally among its 3 descendants. And you end up with 0.46 for this particular node. So notice, right, this 0 ends up with a pseudo count of 0.46, even though its count is 0, to be contrasted with this other 0 in topic, say 9, it ends up with a pseudo count of 0.14, so it's almost 3 times less. And that's the big difference between the Sparse Backoff tree and the Dirichlet, right? So in the Sparse Backoff tree, if you have a lot of non-zero neighbors, like topic 6 does, you can end up with higher probability than this other topic 9, even though the actual count is 0 in each case. So as a result of all this, if you get a larger NZ, that's going to make not just that particular topic more likely, but also its neighbors. And if you do a bunch of sampling over this kind of structure, you're going to end up with related topics clustering together in the tree, right? Because if 5 occurs in a document, other topics that also occur in that document are going to gravitate towards topics 4 and 6, right? And if you iterate this process, you'll end up with a hierarchical organization of topics. All right, so now, right, and this is, so we can achieve hierarchies with this, but what I was promising, right, is that it would scale. So why does it scale? So let's return, this is the Latent Dirichlet Allocation sampling expression. If we compute this naively, so for every token, we're going to go through all the possible topics. If we do this naively, we're going to actually have to do one multiplication, right? One computation of this thing for every topic and every token. And that becomes intractable, right? If we have a large topic space and a large set of text. In recent work, right, there have been methods to exploit sparsity. So the fact that a whole bunch of these things in the numerator, the numerators, are 0, in order to do this much more quickly. So sparse LDA is this Yao et al. Paper. Alias LDA won the best paper award at KDD a year ago. It's also a fast way of doing this flat topic modeling. So at first blush, you might think, well, the complex tree structure is actually going to make computing this product a lot harder. And for existing hierarchical models, that has often been the case, right? The sampling is more complex. But for the Sparse Backoff trees, sampling actually becomes easier, right? And that's the sort of remarkable thing about this. So here's what happens. We have 2 Sparse Backoff trees, right? This is the one that tells us what the document tells us about the topic. This one tells us what the word tells us about the topic. They're different, right? Their counts are different. Our task is to multiply these things. All right, and I'm not going to be able to go through this in sort of a lot of detail, but I can give you the basic flavor, so the sort of trick that makes it fast. The way we're going to do this computation is by recursively walking these 2 trees. And we're going to cut off the search. So we're going to try to walk these trees to end up with this product that we need. But we're going to cut off the computation whenever the sparsity allows us to conclude the total probability mass below a given level of the tree without actually getting into the hairy details that lie there. So here's an example. So as we're recursively, simultaneously walking these two trees, we have to process this node and say, what's the probability mass of each one of these options? We could go left or go right from this node as we're building the sampling distribution. What's the probability of each one of those? We can think of this red tree as consisting of two parts, right? It's all the non-zero stuff, so these counts that aren't zero. There are 3 of them, plus some amount of probability mass that comes from this uniform smoothing, right? Where this node took away from the non-zeros and gave back uniformly to its descendants. And right, this blue thing is the same deal over here on the right-hand side. So we have these 2 expressions that look more or less like this, and then we multiply them out, and here's what we end up with. So this first product is complicated. So if there are non-zero paths going both, for both trees, then we actually have to go down and do some work and determine where they intersect. But fortunately, that doesn't happen very often. In all these other cases, where the smoothing is, where we're multiplying by uniform smoothing, we can actually summarize the probability mass. We can compute the probability mass of each one of these cases without descending anymore in the tree. Right, so if you tell me this thing does uniform sampling and these non-zero paths have a total probability mass of x, then I can say, what's the probability of this whole thing? Well, it's the uniform sampler times x, right? And I'm done. I can stop. And so the fact that 3 of these cases end up being really simple and only 1 requires recursion is what allows this thing to scale to large sets of topics. Okay, so there's a little bit of fine print, and I'm not going to talk about this, but we did have to do some work. So just to get to this point, where there are 2 sparse Backoff trees, like the one I showed you, where it's uniform smoothing across all these nodes, we had to do a little bit of sleight of hand. And that's what this is. And the one thing I'll say about this, and I don't want you to try to understand the details for this talk, but one of the things we do is we multiply, when we're actually computing the smoothing for one of these 2 distributions, we actually multiply the amount of smoothing. It's not uniform in actuality in the model. It's actually proportional to the marginal probability of that topic. And that trick then, after normalization, allows us to end up with uniform smoothing that's similar to that, what I showed on the previous slide. The nice thing is that multiplying by the marginal probability might be a good thing to do anyway, right? So, and this is something people have found in language modeling, that actually, if you don't back off uniformly, like a Dirichlet does, but you instead back off to some kind of marginal probability of the topic, or in this cat smoothing, right, with language models, is a probability of a word. Like you estimate the probability of a trigram in terms of its constituent bigrams. That tends to be actually a pretty good idea anyway. So that's, that went by too quickly for it to really be understood, but I wanted you to know there is that trick under there, and we're using this sort of back off to the marginal, and that seems to work well. All right, some experiments, and then I'll show you guys an application, and then we'll be done. So here's our results showing that it scales, right? So we're plotting runtime versus the size of the model in terms of number of topics. And our goal was to make this thing scale as the number of topics got large. And it does, right? We're paying more. So these are the 2 sparse Backoff tree models, the gray and black. They are more expensive for small numbers of topics. So if you really want to use 100 topics, you wouldn't probably want to use this thing. But as the number of topics gets large, these things scale pretty well. These 2 other, so this purple line and the orange line, are other hierarchical models. This is the kind of story about how they don't scale that well as the number of topics gets large. By the way, but this is a log-log scale, right? So small differences up here near the top are actually pretty important. This blue line is for reference. So this gives you an idea of how well the sparse Backoff trees are scaling. So this blue line is actually the square root of the number of topics, proportional to that. And you can see actually the sparse Backoff tree models are increasing less quickly than the square root of the number of topics. So it's strongly sublinear. Sparse LDA, which is one of these fast, flat topic model approaches, is faster than us. But the interesting thing is, as the topics get really large, you actually see a larger slope on the sparse LDA line than you do for the sparse Backoff tree lines. And that's, in principle, the tree-like structure ought to allow you to perform faster inference even than a fast sparse flat model. Although we're certainly not seeing faster yet, but we do see that difference in slope that's encouraging. All right. Right, and so the other thing is, why are we doing this? Why do we want hierarchies? Because it's more accurate as the number of topics gets large. Here we're measuring accuracy in terms of perplexity measure. That's just how accurate is the model at predicting held out text. Lower is better. And as the number of topics gets large, these sparse Backoff tree models do actually do well. We're working with two different versions of sparse Backoff trees. One's like, this is just sort of to qualitatively sample the space of different architectures. One's large and wide, and the other is skinny and tall. And they both kind of do relatively well. The skinny tall ones, I think, a little better. And the overall perplexity, right? You get much better perplexity with large numbers of topics. In particular, larger ones. So this is a relatively small corpus. This is like 3 million words. And you can actually get a much more accurate model if you use thousands of topics, which most people wouldn't do, right, in practice for a corpus of 3 million words. Now we're talking about large corpora, where large should probably be in quotes here. These are order of magnitude 100 million things. So RCV1 is 100 million tokens of Newswire, give or take, and WPL is 80 or so tokens of Wikipedia links. So this is like the Wikipedia link graph. We're trying to do a link prediction task. And again, right, as you scale to large numbers of topics, you get more and more accurate models, lower and lower perplexity, and these SBT models are more accurate than LDA. And in this set of experiments, we actually couldn't get, so even with sparse LDA, we couldn't get to the large topic sizes. In this case, it was actually due to memory limitations. So sparse LDA for these corpora and 100,000 topics used more than 256 gigs of RAM. Yep, sorry. Oh, great question. Yeah, so I kind of skipped over all this. It is sensitive, but we tried to make the best choices of hyperparameters as we could for both methods. So this LDA thing is McCallum's sparse LDA package. It does re-optimization of the hyperparameters every so many iterations. So we are actually, and if you don't do that, you can actually get really bad perplexity. It's like really easy to turn this alpha knob and actually make these things really bad. But we're doing this re-estimation. This is kind of as good as we could get for LDA. And for the sparse Backoff trees, we're doing something very similar. So we also re-estimate the delta parameters every so many iterations, and we do that. In the current version of the code, we do that using a gradient descent technique on likelihood. In these experiments, we were doing something slightly different, but it sort of amounts to the same thing. So I guess the short story is it is sensitive to the parameters, but that's actually why you need to re-optimize these parameters in order to maximize likelihood, and that's what we're doing. And so I don't think it matters too much what the initial settings are of the parameters, but you do have to do this re-estimation. Oh, yeah. So good question. We are actually doing it like this, right, where we have the same delta at each level of the tree. That's what we did. We could relax that, though. So, I mean, all the algorithms work fine, even if you relax that. And it might help, right? It does make, right, it makes this sort of parameter space larger. I'm not sure what would happen. But we did, yeah, we made just more for simplicity than anything else. We made that, that simplifying assumption that all deltas at a given level were the same. Yeah.
Another question more empirically. I'm wondering if you just go to the previous slide. It seems, as you pointed out, right, the perplexity goes down as the number of topics increases, and you can't even get there with flat LDA. But I'm wondering, is that really better in the sense that it seems intuitively like there's a cost also associated with having more topics, no?
You mean a cost on kind of the user, the consumer of these topics,
exactly,
who's going to try to learn about that?
Actually better?
Okay, yeah, so for how topic models are typically used, yeah, maybe you know, if I have a corpus and I want to say understand what's in here, I think we would at least need new visualization tools in order to help us deal with 100,000 topics. I do think there are actually, you know, there are insights you can get out of these large sets of topics, and I'll show you an example in a second that you actually can't get from smaller sets. Although, yeah, we would need new tools to be able to really use these for document browsing and sort of understanding a corpus. The thing I would say though is, I mean, this is what I care about, right? Because I want to build accurate language models that can predict, you know, unseen text, you know, throwable objects such as X. I want to know what X can be. And so this, you know, pushing these numbers is sort of what is important to me. But yeah, but for typical users of topic models, yeah, how exactly would they consume these large things? I think we would at least need new tools. Here's an example that shows, you know, something you can get when you have these really fine-grained topics that would be hard without that granularity. So this is the 100,000 topics over Wikipedia links. We took the most associated terms with each one of these topics. We found this part of the tree. So, and this I just started kind of on the left of the tree. So these topic numbers are actually, you know, on left to right from 1 to 104,000 or whatever. And it seemed like this particular node was all about radio stations. And then, so all sort of 1,000 topics or so below it were all about radio stations. And these particular ones, the most associated concepts were all these 4-letter, you know, call signs of these individual radio stations. And radio stations with related content or in similar places tended to be clustered together in individual topics, right? So all of these are Tennessee stations, all of these are Tennessee stations. You know, and these are North Carolina Christian AM stations. So it's very, very fine-grained. More generally, right, all 6 of these are stations in kind of the southeast of the US, more or less. So this is the kind of thing, right, that you could get. You can find these fine-grained distinctions, and they seem to fall within, you know, more coarse-grained, broad groups. We need to do more investigation of these trees.
I'm curious a bit
Yes.
about the tree versus a multidimensional space. It looks like you have like, if you have multiple dimensions that
Yeah.
kind of mashed together.
That's right.
North Carolina versus Tennessee versus Wyoming, and this Christian versus Spanish versus what?
That's right.
AM versus FM versus whatever. So would
Right.
it be like more interesting or as well as interesting to try to tease out these dimensions?
Yeah, you're absolutely right. So there's this sort of implicit assumption here that you know, nodes in this tree inherit properties from their ancestors, right? And what you're saying is actually, you know, it doesn't have to be a tree. It could be more like a graph where properties are kind of, what we really care about are the properties. I completely agree. Yeah, so a richer model that does that would be better. It's, you know, a harder problem to solve, but definitely worth doing. Okay, so briefly, I want to show you guys an application that we've built recently that can use this, in particular, this Wikipedia link graph prediction technique in order to provide some sort of interesting visualizations. So I'll just do this real quick in 5 minutes, and we'll stop. So this is this idea is actually the brainchild of Brent Hecht, who I mentioned earlier, who's at the University of Minnesota. He was a geographer as an undergrad, was a computer scientist at Northwestern as a PhD. He really likes maps. There's a handful of things that he likes about maps. So when you look at a choropleth heat map like this, you can get a lot of information. So you can get specific information. This is plotting median income over the US. You know, certain states fall into certain buckets. That's the specific information. And then you can also get this regional information, like, you know, the northeast of the US tends to be higher income than, say, the southeast, right? Now, it'd be great to be able to visualize these kinds of information for arbitrary queries, right? So if I just want to know, tell me about nuclear weapons, how is that related to different places on the map? So with existing tools, I can't really do this that well. So if I go to Google Maps, and this is a little bit stale, it might be better now. But if you go to Google Maps, you ask for nuclear weapons, you get a handful of places. They're not, you know, they're relevant, but you're missing a bunch of stuff, right? So there are all these regional effects, like, oh, you know, there's this whole region that's kind of relevant to nuclear weapons, right, in terms of controversy about, you know, who has them, who should be allowed to have them. And then the history of nuclear weapons, right, in you know, the former Soviet Union, there's no sort of locations there. So in terms of getting a heat map about nuclear weapons, this standard Google Maps solution doesn't do that for us. So this is an application we built called Atlasify, and I'll show you how it actually, so it mines relatedness values from Wikipedia. I'll say exactly how it does that in a second, but let's search for nuclear weapon and see what happens. So here, right, we get sort of a much more filled in heat map, and we do get, Russia's very related to nuclear weapons, all these sites in the US. All this information now, this relatedness, is mined from Wikipedia, and you can search for any Wikipedia concept for this application. Yeah, so Iran is there. It should probably be more, it should probably be darker. And we're getting, so all this information is from Wikipedia rather than, say, Newswire, right? If it were from Newswire, it'd be darker. But we can see, so let's actually click on Iran and see what, see if we have explanations. What? Looks like I misclicked. Well, let's check Saudi Arabia for now, see if we get anything. All right, so Saudi Arabia, right, there's this passage. So then you can click into these things and dig into why is it related to this. And this is talking about, this is a particular sentence that's grabbed from Wikipedia, right, that says, and this is about, fears that Iraq would use nuclear weapons on Saudi Arabia, right? And so that's one way that Saudi Arabia is related to nuclear weapons. Not so much that they have them, right? But instead that, there was concern that Iraq would attack them with them. Okay, and so why don't you guys give me one more query, and then I'll stop. So what do you want me to search for? Apple pie? That's a great test, right? If we don't get a lot of activity in the U.S., we're in trouble. Okay, so yeah, we do okay. There's lots of particular locations in the U.S. that are related to apple pie. Yeah, that's a good question. I don't know. Let's find out. And then one more try. There we go.
Then I wanted to try cricket too.
You want to try? Okay, we can definitely. I think we can do pretty well in cricket.
Available online, right?
Yes, you can try all this stuff, right? Yeah. So yeah, please. So atlasify.com is this URL, and you can try it. So yeah, this is so cinnamon, right? So I guess that's one of the reasons, right? And cinnamon comes. How's that related to China? China's cinnamon has been known, right? So China's like sort of I guess the birthplace of cinnamon or something in some sense. And it's also used in apple pie, so that's one of the ways they're related. And notice, right, you see some sort of weird relationships here. So this is not a heat map that sort of talks about the total consumption of apple pie in that country, right? What you're seeing is kind of a relatedness measure that's based on how often these things are mentioned together. Apple pie is a good one. I can switch to these other, so once you can do this for the world map, right, you can do it for anything. And so we also did this with the periodic table. And here are a handful of things that are related to apple pie on the periodic table. And I don't know, we often don't get explanations for these, especially, oh yeah, okay. So apples, wow. I'm not exactly sure what that tells us about iron. But okay, apparently apples, right, maybe contain some iron, and that's part of the reason why they're both related, or part of the reason why iron is related to apple pie. This, you get more striking things with this if you search for, say, right, nuclear weapon. You'll get sort of what you expect, like the bottom row ought to be very related. Yeah, so the bottom row is the most related. Okay, so that's Atlasify, yeah, and I encourage you to this nuclear weapon design. Encourage you to play with it if you're excited. So these are the folks that were involved. Are really awesome. So it was built mostly, the front end mostly by University of Minnesota undergrads who did an outstanding job. Also some folks in the web sale team, like Chandra just fixed actually a bug last night that allowed me to do that demo. So that was good. So, okay, and so here's how this works. What does this have to do with probabilistic models of Wikipedia content? Well, of Wikipedia links. Well, here's why. The way we're estimating the relatedness of two concepts is based on the fraction of pages that link to both of those concepts. So if there are a lot of pages that link to both X and Y, we say X and Y are related. And this actually works fairly well for general concepts. So that's the coloring in the Atlas of Phi map uses a quantity just like this. If we have better probabilistic models of these things, we can do a better job estimating what map elements to color which colors. Here's a Seattle example, right? Very related to Chinook salmon. Every place is kind of related to goldfish, but Seattle not so much to catfish. Okay. So finally, future work, we want to generalize. So these sparse Backoff trees, we talked about how to apply them to a latent Dirichlet application where you have two multinomials that you're multiplying together. You can actually do that for n multinomials. And the code that does this is already available, so you can download that if you want. We're using that right now for hidden Markov models where you have information from the word and the foregoing context and the previous context. Right? So you have three sources of information. You have to multiply all three of those. You can use the same approach for that. We're experimenting with that. Not exactly sure how well it'll work. And then, right, one of the things we want to, I'll just show this really quick. We want to enable these ad hoc reference systems in Atlas Phi. So in addition to the world map periodic table, we'd like people to be able to define their own reference system. So we say, I want rock here, hip hop, and country, and then plot me all the Grammy Award winners on this thing. And this actually should not be hard to enable given the semantic relatedness measures that we have. And so this is actual data from the semantic relatedness measures. We just haven't made this publicly available yet. And these relatedness measures do okay. So they'll put Jay-Z close to hip hop and Tim McGraw close to country. So that's one of the things we're working on Atlas Phi next. All right, thank you very much.